All right, now we're going to discuss dipole-dipole forces. It's the second in this series of the intermolecular forces that we're going to talk about. It's the next strongest compared to the van der Waals forces or the London dispersion forces. Dipole-dipole forces now occur between compounds that actually have a dipole. Previous compounds were nonpolar compounds or did not have a dipole, but these compounds do have a dipole. So it's not a temporary interaction. You will actually always have an interaction. Okay, so the dipole-dipole interaction results from the approach of two polar molecules. If their positive and negative ends approach, the interaction is an attractive one. All right, that we already know. If two negative ends or two positive ends approach each other, then it's repulsive. In a liquid or a solid, the molecules are most likely oriented with the positive and negative ends together, and the net force is attractive. So basically, this whole slide is talking about if you have a polar molecule, let's just say we have like CF, let's put like CH3F. All right, you have your partial negative on your fluorine, your partial positive on your carbon. And that will always be, all right, because fluorine is much more electronegative. So if you have another fluoromethane, that's the name of the compound, partial negative, partial positive, this fluorine is attracted to the carbon. So you're going to have the dipole-dipole force between the fluorine and the carbon. And this fluorine will be attracted to another carbon, and this fluorine to another carbon, this carbon to a fluorine. So you'll always have these interactions. Okay. Now notice you also have hydrogens on here, but you know that the carbon-hydrogen is a nonpolar bond. Okay, so you do actually have very small London dispersion interactions of the nonpolar ends, but usually you don't talk about that because it's much weaker of a force than your dipole-dipole force. So you technically have both a dipole-dipole force between here, and you also have a London dispersion force between this and another hydrogen on another compound, but that force is so small that it kind of is not even important compared to how strong the dipole-dipole force is. All right, so here's an example. I just already did it, but here's another example. All right, this time of a chlorine, same type of thing. Your chlorine is partial negative, your carbon is partial positive, so the chlorine is going to be attracted towards this carbon. The chlorine is attracted towards that carbon. All right, again, you're going to have opposite charges attracted towards each other. These are repulsive forces, so obviously that won't happen. So your interactions won't be between a chlorine and a chlorine, it's between a chlorine and a carbon. All right, the next one we're going to talk about is hydrogen bonding. And hydrogen bonding is actually a type of a dipole-dipole force. It's a special type of dipole-dipole force. You have to have a polar bond, and you have to have a hydrogen. And the hydrogen is usually between a lone pair. Okay, so one, this is the strongest of all of the dipole-dipole interactions. All right, so between the three intermolecular forces we just talked about, the London dispersion is the weakest, then dipole-dipole, and then this hydrogen bonding is much stronger, but again, it's a type of a dipole-dipole, but it's the strongest type of a dipole-dipole. It's between organic molecules, and it must have an NH or an OH to be able to form a hydrogen bond. Okay, you know, you could also have an SH. They don't talk about it because it's not as common, but pretty much what you need is you need a lone pair on the atom that has the hydrogen on it. Okay, a lone pair on the atom that has the hydrogen on it. Okay, because this makes this very partial. I mean, this is very partial negative, and this is very partial positive. Right? Sometimes a little pair. You can also have it between HF. I don't know if the slide talks about it. We'll see, but you also can have it between HF. HF forms hydrogen bonds as well. Okay, so the hydrogen for one molecule is strongly attracted to the lone pair of the oxygen or the nitrogen. That's why you have to have a lone pair. OH is more polar than H, so alcohols have a stronger hydrogen bond because your partial negative charge is much greater. So your dipole, you have a much larger dipole here than you do between your nitrogen and hydrogen. Okay, so you still have a hydrogen bond, but now you have a degree of how strong the hydrogen bond is. Okay, based on the electronegativity of the atom. So here's some examples. One is of methanol. All right, methanol has a hydrogen and an oxygen. All right, this is a type of alcohol. We'll talk about functional groups next chapter. But basically, the lone pair on the oxygen is attracted towards the polarized hydrogen on another alcohol. All right, and technically you have two lone pairs, so you can form hydrogen bonds with all of those. Okay, you can form another hydrogen bond here. So you can see a network. This will form a hydrogen bond with an oxygen lone pair. So you can see this huge network of hydrogen bonding. That's what makes it pretty strong. Okay, now you also have a partial negative on the carbon, so the carbon actually can also form its own dipole-dipole intermolecular force with another oxygen molecule. But again, it's much weaker than the hydrogen bond, so we just kind of ignore it. All right, here's an example of a nitrogen lone pair to a polarized hydrogen. Okay, so those are hydrogen bonds, very specialized. Now, boiling points are based off of the intermolecular force. Okay, you can predict boiling points of compounds based on how strong the intermolecular force is. The stronger the force, implies higher boiling points. Also melting points. All right, but I believe they just talk about a boiling point. Okay, so here you have isomers. Right, you have constitutional isomers, same formula, but a different compound. You have an alcohol. All right, this functional group is called an alcohol. It's got lone pairs. It can form hydrogen bonding. This is called an ether. This just has lone pairs, but it forms a dipole-dipole. It does not form hydrogen bonding. And look at this. It's a difference of about 103 degrees from positive 78 to negative 25. That's a huge difference. So it just shows you that hydrogen bonding has such a huge effect on the molecule. They both are dipole-dipoles, remember, but hydrogen bonding is a special type of dipole-dipole. So hydrogen bonding increases the boiling point. Here's another example of an alcohol, this time of an amine. This is called an amine functional group, but same thing. You have hydrogen bonding. So you have hydrogen bonding here and hydrogen bonding here, but because this is more polarized, you know, you have a huge difference here, almost 60 degrees of a difference in boiling points. Okay, so H is more polar than H, so alcohols are stronger hydrogen bonding, therefore higher boiling point. Okay, here's some problems. Why don't you go ahead and rank these in order of boiling points, all right, and explain your reasoning. Put this on pause and do the problem, and then when you turn this back on, I'll go over the answer. All right, you should have been on pause. All right, so let's go to the next slide. We'll talk about the answer. Well, actually, we don't have to worry about that. This is pretty straightforward. Okay, there's a lot going on. First of all, the highest boiling point is going to be one of these alcohols. They both have hydrogen bonding. However, what do you think is higher? One that's straight chained or one that's branched? Well, we talked about branchings have lower boiling points. So not only do you have hydrogen bonding, but now you also have the increased London dispersion force plus the higher surface area. So this is going to be the highest of the boiling points. This will be the second because of hydrogen bonding. Now you have three that are not hydrogen bound. You have higher surface area. So this will probably be the next in boiling point, right? And then you kind of have these two. This is technically more branched, all right, than that one. It's kind of hard between these. I would say they're pretty close to each other, but based on the surface area issue, I would say this would be next in boiling, followed by the neopentane as the fifth one. Okay, and sure enough, that's exactly what we see. The pentanol, they have an opposite of what we did. The pentanol, the alcohol, the straight chain alcohol, is the highest followed by the branching. I'm just going to do these quick. Followed by the N-hexane, which is more surface area, the 2,3-dimethylbutane, and finally the neopentane. All right, so if you got that correct, you understand boiling points and intermolecular forces.